Hello. Hi, good afternoon. Well, I'm very pleased to. Yeah, can you hear? Yes. Today's Art and Technology Society is giving these presentations together with Anil Yaman. Thank you very much for coming. Anil will make an introduction to artificial intelligence and what are the society implications of it. And then I will give you a little bit introductions about the background of Anil Yaman. He has a bachelor's and master in science degrees, and he studied and worked in the United States, especially in the Department of Biomedical Information at the Columbia University. And now in the last year has been a PhD candidate at the University of Eindhoven in the Department of Mathematics and Computer Science. His areas of research interest are evolutionary computation, artificial neural networks, and swarm intelligence. And I hope you can talk about your project Phoenix, which is about exploring the unknown through reincarnations and co-evolution. Thank you very much, Anil. Wait a second. Sorry. I made a mistake. I want to announce also the next events of this month of Art and Technology Society. Our next event is going to be next Tuesday with people interested to use art and technology as enablers of social innovation. So you are welcome to join as well. And it's come. Then we have a creativity workshop with Hans Glockhaus, on Thursday 16. Also, if you're interested, please contact me or contact. May, sorry. And then on 30th of May, we have human artificial intelligence cannot replace. So also, if you're interested, please. Yeah. Yeah. Oh, sorry. May. It's May. Yes. No, yeah. You're right. Sorry. And the next one, I'm organizing also artificial workshop for non-technical professionals. I'm in the way to deal with that. So if you're interested, please let me know so I can put you in the list. And finally, we are also co-organizing the Science Hack Day on 25th and 26th of May. So 2 days full of creativity and innovation and inspiration. So, yeah, if you want, please join us. And yes, now the
yes.
Thank you.
Thank you very much for the introduction. I'm very excited to talk to you about this topic today. Can I have the slides, if possible? Yes. So basically, I will give a presentation about in two parts. First part is about introduction of artificial intelligence, and the second part it's about its implications to science, engineering, and also society. So my name is Anil Yaman. I'm a final year PhD student, and I specifically work on nature-inspired artificial intelligence. For example, I look at biological systems and organisms and that seem to produce intelligent behavior and try to model this in artificial systems. So this talk will be a bit biased towards this view. I hope it will be interesting for you as it is interesting for me. So since we are talking about artificial intelligence, we already kind of dichotomizing the word intelligence. And for example, I have my favorite quote here from pre-Socratic philosopher Protagoras, where he said that man is the measure of all things. Although it might seem a bit sexist, but what he means to say is that everything is actually relative, especially relative to humans. In this case, also intelligence seems to be relative to humans. For example, most of the people consider intelligence as being the cognitive capabilities and problem-solving capabilities of humans. But today I will mainly discuss that actually intelligence is exhibited in many various biological organisms and systems, and also in different forms. Of course, there are some overlaps. For example, I don't mean to here provide a taxonomy of intelligence, but I would like to give some examples. First is theory of mind, which means that we have a model of ourselves, our desires, intentions, and beliefs. And also, on top of that, we have also a theory of other minds, a model of other minds, where we also know or understand that others also have certain intentions, beliefs, and desires. And also we take into account these during our decision-making processes. And another example will be communication. Human beings have quite high level of communication, which is language. But we can also see in many different biological organisms or animals a way of communication. For example, here research suggests that honeybees can signal the orientation and the location of the food source by making use of this vaguely dance, what is called. And basically communication serves these animals or biological organisms to align with the other group members or members of the species. And another example of intelligence is the use of tools, which means that to manipulate or engineer certain objects in the environment in order to achieve certain goals. And another interesting concept is actually swarm intelligence, where a collection of agents come together. Actually, they themselves do not seem to have high level of cognitive capabilities, but when they come together, they exhibit quite sophisticated capabilities of problem solving. So in this case, I give the example of fire ants that can close a gap between two places using their alive bodies. And another example would be biological immune system, where it consists of some number of different specific cells that themselves are highly specialized for certain tasks. But when the system comes together with many of these cells, they even exhibit memory and learning capabilities. And also we can extend this idea to our bodies or other biological organisms. We also consist of many billions of cells that collaborate with each other to keep us alive. So, or also brain consists of many billions of neurons that can learn efficiently how to map sensor input to certain behavioral outputs. So in these terms, I can make a general definition of intelligence, where I would say that it's an innate or acquired perception action patterns that allow an agent or collection of agents to achieve its or their goals. And usually it exhibits some learning and memory capabilities. In this case, for natural beings, of course, the ultimate goal is to survival, and intelligent behavior is a process of evolution that emerged to allow individuals to solve their problems they encounter in their environment. So what is artificial intelligence then? We can say that it's the study of producing or mimicking intelligence in machines. So here I depict one artificial entity. This is humanoid robot, but an artificial intelligent agent does not need to be a robot. It can be any, for example, software agent or a computer. However, it functions within an environment. It can perceive the environment and perform certain actions. And while it is doing that, it has a mechanism to understand what kind of the state of the world currently, and then produce the action that can make it achieve its goal. And it can have a certain knowledge base. Depending on the implementation, it can be different kinds. But basically, we can store certain number of actions, and it can pick one of the action that is most suitable for the for the current state of the world. And artificial intelligence usually classified in two broad categories: narrow, weak AI, or strong AI, which is already also known as artificial general intelligence, AGI. So for the narrow AI, it is limited to specific domain. So currently, what we have right now today, all AI systems are basically narrow AI. We can enumerate many examples of this: search engines, spam filters, chess playing agents. Even autonomous cars, they are very sophisticated technology nowadays, but they still are highly engineered to handle only a driving car in a, for example, navigation task. Although the task itself is quite complex and there are many uncertainties, but still it is limited to this domain. But for the AGI, basically it is usually referred as the agent that can perform or exhibit as the human level problem solving capabilities, basically. And it can perform, in this sense, broad range of tasks successfully. And here we assume also a concept from philosophy, physicalism, that related to multiple realizability, where we assume that this is possible only if we can mimic human intelligence with, for example, also with different materials, basically. If this is not the case, then, for example, we may need to use neurons. Maybe they have specific properties that make it more high, that can achieve high-level intelligence. But for our software, we are assuming that it is possible to also mimic this using, for example, silicon-based computing. And we also have many examples of that, but only from movies. In this case, we have an agent from the movie 2001, A Space Odyssey, HAL 9000. And in this movie, for example, it was managing all the functions of the ship. But they were, when the movie was produced, they were thinking that this level of intelligence would be possible in 2001, but we still do not see it yet. And I would like to mention some approaches how to build an AI. In right now, what kind of approaches that we use. Here also another quote from Dijkstra, where he said that the question of whether machines can think is about as relevant as the question of whether submarines can swim. So it is still pointing out that we can assume that there is multiple realizability. We can maybe imitate not using the exact material or exact methods how nature provides intelligence or other functions, but maybe not exactly same manner, but using different material or different methods. Also within these methods that I will mention, they can also simulate intelligence maybe similar ways. Maybe they have limitations and advantages among each other, but they nevertheless can perhaps simulate the same level of intelligence. First example is rule-based systems, also known as expert systems, where we acquire expert knowledge and formalize it and store it into certain knowledge base. And the users can query this knowledge base through this user interface. And basically, inference engine can match these queries and infer some additional knowledge within this logical framework and answer as advice or result of this query. And this is generally known as medical diagnostic decision support system. Another example is machine learning nowadays, which do not right now we are not extracting knowledge, we are not formalizing knowledge, but we are building models that can learn itself from data. We only provide the data for the model, and it can be in different categories based on our data. So, for example, for the supervised learning case, we have the data completely labeled, meaning categorized, and then we learn from data what the data input is and what kind of class that it belongs. And these models generalize this data, and when we have data that is not classified, we can use this model to assign a predict or a label. And another example is unsupervised learning, where in this case we don't have data, but we can use clustering approaches, for example, to find similarities between these data points. And another example, reinforcement learning, where in this case it's a model of more human learning or biological learning that happens in biological systems. For example, in human child, for example, it can learn itself while experiencing, by interacting with the environment. If it burns from fire, then it learns that it's a punishment, then it learns that never touch again. So similarly, we can train agents based on experience with reward and punishment signals. Another example is search, and in this case, we represent possible current state of the world and all possible states that we can achieve by, for example, enumeration. And basically, in this case, we tic-tac-toe game. When we represent that our state of the game right now is like this, then we can enumerate all branches possible ways that algorithm can take and find the branch that leads to most successful outcome. And this is generally used in all games, most of the games, for example, chess. But some of the games, of course, that have high complexity have quite large amount of quite big, large search space. Thus, it might not be plausible to search this space in real time. We need to do maybe more. So here I would, this is the final approach that I will mainly focus from now on. This is nature-inspired artificial intelligence, specifically evolutionary AI, where we use evolutionary process as an inspiration to build agents to perform certain tasks. So in this case, for the evolutionary process to function, there are three main principles. First, it needs inheritance. So basically, the offspring should get some or maybe most of the characteristics of its parents. And second principle is basically the reproduction with variation. In this case, the offspring is not getting all characteristic, but there is some variation where with that we explore the search space, possible designs we can come up with. And then the final step is selection, natural selection in this case, which is a natural filter that eliminates the individuals that do not fit, and most successful one remains. Successful ones remains and reproduce. So with given enough time, it can produce high complexity and the agents that produce intelligence, as we see in natural life. And here is an example to demonstrate how it is done in artificial settings. For example, here we have an artificial creature that we would like to find optimum behavior as bipedal walking. And we can define a strategy of walk for this agent. Basically, the strategy of walking, a sequence of muscle movements. So we can define that. And of course, we don't know what the optimum muscle sequences are to provide this walking behavior. But what we can do is that we start with random population, random walking strategies. And of course, we don't expect that anyone will perform good walking. They will probably be very, very bad. But we know that some of them among this population will be better than others. So we take those, for example, we reproduce them with certain small variation. And then we do that iteratively some number of times to achieve satisfactory behavior. So this is an example of this, where in the first generation, we will see in a minute, that first generation doesn't perform good at all because it doesn't go that far. But 20th generation, it performs a bit better than this. 80th generation, it's even better, but still not very good. But after we perform this iterative process for 999 times, then we have quite robust behavior of walking. So this is modeling or inspired from evolution. We can generate these kind of behaviors. And also more examples of this. They also did for humanoid forms, for example, there with different shapes. And also it is even robust enough to walk incline, and it can tolerate certain disturbances, but of course it has only some range to tolerate. After trying this big block, it cannot walk anymore. And not only for walking, we can also apply this in any kind of system that we want to find intelligent behavior. In this case, they are training artificial neural networks using this evolutionary idea to play a Mario game. So in the first generation, the agent randomly initialized, and it's not really efficient in playing the game. But in third, fourth generation, it shows some improvement, and it can play quite nicely. And for the conclusions for this part, I would remark that based on this, artificial evolution is quite powerful method and mechanism to produce intelligent behavior in agents, basically in artificial agents. And I would still outline the missing part, which is maybe evolution of learning. So I myself also work on that. Right now we can find really agents that are optimum for certain tasks. But what about, for example, learning over during their lifetime? So for example, for the biological neural networks, it's also learning in biological neural network is a product. This is also mechanism and product of evolution. And can we mimic this learning in really artificial settings? For example, in biological neural networks, they have this research suggests that the learning algorithm is more like a local base. It's based on the local interaction of neurons. So can we imitate this behavior in artificial neural networks to produce, for example, lifetime learning for artificial agents? So thank you for this part, for listening. This will be the conclusion for now. If you have any question, please. Yeah. So there are approaches. For example, one approach is basically everything is genetic. So my behavior is completely defined by my genetic code, and I don't learn anything. I just do whatever my genetic code prescribes beforehand. And in this case, what knowledge transfer from one generation to another generation means that only my genetic code plus some variations, then my offspring will do similar things mostly like me, but a bit different maybe. So this is completely genetic. But other case would be, for example, also known as Baldwinian effect, where the individual themselves can also learn during their lifetime. So we need to find a way to encode this mechanism in the genotype to allow this behavior. And in this case, now if you consider evolution as searching this possible search space of individuals, with the Baldwinian effect, basically, we add another complexity where we are only looking at one point in the search space, but this point during their lifetime can change their place in the search space because they adapt themselves based on the environmental conditions. And this is more like epigenetic evolution, where everything is not defined by genetic, but also from the nurture, like nature and nurture kind of trade-off. Does it answer or?
New paths.
So many artificial intelligence algorithms work well to a certain point, so require humans to help them. We saw that in the self-driving cars when people have the auto drive on and there have been accidents.
Yeah.
Or say for medical images, to identify organs, you still need a human to go through and edit.
Yeah.
What do you think would be the best approach to overcome those problems? Like, is it necessary to use a mixture? Do you think that your mimicking learning behavior will help the algorithms improve more?
Yeah. So in this case, of course, we have this. We are optimizing the algorithm for certain situation, for certain test case. So it achieves best result in this test case, then we are satisfied with it. And if we know how much error that it would likely make, then we can prepare for that. And if a decision is given, then we can say that maybe there is this much error possibility. And then we can check if this is the case or not. Yeah, I think in the second part also I will discuss a bit more on how to make it better, kind of, and also how to make it safe or better. But I think this is what I can say about this. Mostly more testing and validation, maybe. But still, human might be required for certain tasks.
What's the state-of-the-art artificial intelligence at this moment?
In which definition? Like
artificial
general AI, artificial intelligence, or?
Yeah, AI, computational.
So basically, what can be done is with the narrow tasks. Most of the tasks they can perform. The artificial intelligent agents can perform better than humans. For example, chess playing or Go playing or autonomous driving, less error, or face recognition, traffic sign recognition, like computer vision. These tasks, they have all better performance than humans. They can recognize even better than humans. But that's about it. It's about accuracy. But for the artificial general intelligence, there is no kind of self-learning in the sense of changing your motivation or finding out different perspective, like creative learning. So these still, and common sense learning, for example, they cannot really provide common sense reasoning. So these are the things that are most problematic for now.
But if you consider task-based artificial intelligence, then the machine can still improve. So that intelligence is improved. Yeah. Although you cannot compare it to human intelligence, but for that specific task, there's an improved mechanism there, and you can, let's say, improve the algorithm there, and that makes safe driving possible.
Yeah. But also, I mean, it can improve, but it might also degrade because learning not always positive. Sometimes also it can be negative. And also there is all different discussions about ethics. We can discuss in the second part. But yeah, that's true. Basically, they can improve based on experience, based on more data. But then, yeah, it will be only limited for this specific task. So for the second part, I will mainly discuss the implications of AI, especially to science, engineering, and society. I will give some examples, also some of the projects that I work. Of course, it will not be complete list of things because there is many people working on improving in these fields, and AI is being used now in almost every domain. So we can mention a lot, but I will start giving some examples. For example, in some cases, this is also one of the projects that I collaborate with. We have certain models. For example, in this case, we have physical model of mathematical model of molecule interaction. However, these models are very difficult to or time expensive to compute. So in this case, we can use these machine learning algorithms or AI algorithms to reduce this computational complexity by instead of using the model itself, we can use this model that we train based on already given some number of computations, like we know certain interactions and how they behave, and we can train a model based on that. And using this trained model, we can scale it for larger systems. So there are many examples of this as well. From right now, we have very big databases from many domains. For example, biological neural networks, they produce a lot of data. Also, gene-related subjects like protein-protein interaction networks. So in these cases, it is very difficult to find out about the underlying model or find out about interactions. In these cases, we can use these models to identify, detect some patterns, for example, data mining approaches to find out what really some rules that make sense to discover more knowledge. And another interesting aspect is this study where they produce antenna using evolutionary computing in this case. This is the antenna that was found that was optimum for 2000 NASA spacecraft mission. So basically they started with the first generation here with a random shape, and over generation it evolved. In each generation they measure how much radiation pattern, for example, can be emitted using this shape. And over generations, it ended up with this shape on the last generation. The interesting thing is, so this is the optimum, for example, for the left one, it is the optimum pattern for receiving data, receiving radiation pattern, and this is producing radiation pattern. But interesting thing is that they also state that it is not very likely that many engineers would not suggest this one. So it is quite counterintuitive, perhaps. But nevertheless, this was the optimum one. And also, they say that it was possible to find this shape, including the implementation of the algorithm in 3 months of a person work. But if engineer is designing this, it would take 5 months of work. And what they also say is that if the mission is changing, then they can produce very easily new shapes depending on the mission, because different missions require different kind of radiation pattern, apparently, according to them. And basically, if you change the mission, then you can design new pattern only in 4 weeks. After you have the algorithm, it's very easy now to produce new designs. So this is quite interesting to use, for example, evolution computing for these settings. And another application that I work is actually quite a large project. We are working with 7 partners, 7 different universities or institutions. Here, the project is called the Phoenix Project. This is FET Open Horizon 2020 European Union funded project, where what we do is that we try to explore or monitor different to access environments. In this case, different to access environment can mean that underground, for example, pipelines or underground river. It can also be extended in, of course, for the ambitious future work. It can be extended in volcano exploration, or it can be extended to space exploration, any area that is not very easy to access. So in this case, we also use evolutionary computing to find out optimum swarm of agents. Here we use swarm intelligence idea, where instead of using one agent, because it's very difficult to use it, for example, if we use one agent, if you lose it, then basically mission is over. But if we use low-cost, cheap agents, we can use many of them. Even though we lose a big portion of them, it wouldn't matter. We can reconstruct some of the things that we already saved. And another aspect of it, with these limited access environments, we cannot also access with one agent, because usually if you have one agent, it would have high demand of power, high battery requirements, GPS connection maybe, so it will be very difficult. But here what we do is that they have very limited capabilities, low requirements for memory, battery and memory as well. But they communicate locally, and they, with the swarm, they can map the environment. Here, for example, the project is almost coming to an end this October, but we were able to produce this hardware basically, and also we are working on the software to work with these agents, and we will have test case by the end of this year. Another interesting thing, the application also about art, evolutionary art. Basically, in this case, you can also try it in pickbreeder.org. So this is inspired by actually Richard Dawkins' idea of biomorphs from the Blind Watchmaker book. And in this case, we don't have objective function because these art forms are not very quantitative. It's difficult to quantitatively measure how good they are. So it is more like qualitative measure, subjective measure is done by human beings. So basically, each of these images have certain underlying function that can create this image, but a human being is sitting, for example, in front of the computer and saying, okay, this is interesting, then I will reproduce the function of this image with the variation, and it will produce variation of this image. So you can, by selecting and breeding these artifacts or images, you can generate new designs. And if you do that, for example, they provided this to public access, and with crowdsourcing, people were able to generate images, and they found that, for example, these kind of images that come up. And they seem interesting in terms of their similarity to natural or other objects. And the idea itself, for example, we can start with these random images in the beginning, and then by mutating them over time, we can generate all this variation of different art forms or different shapes, images. And now I will discuss about the last part, implications of AI to society and some concerns of AI. Basically, we can mention two things, I believe, unemployment and AI safety. I will discuss more about AI safety, but for the unemployment, of course, we are aware of that this industry of automatizing everything. And also, I've shown some examples, even maybe automatizing design, engineering topics. This might likely take lots of jobs from real humans, basically. But it is at the same time generating new areas. For example, nowadays, machine learning, data science, AI is attracting lots of people to work in these topics. This is also a good thing. But for the time being, I cannot say much about it. I don't know what's going to happen in the future. But for AI safety, we can discuss a bit more. For example, this is the funding going to AI safety for last couple of years. And this is from Future of Life organization, which is intensively involved in this kind of research, AI safety, and it was established by Max Tegmark, for example, and collaborating with Elon Musk and other top researchers in this field as well. And here we can see that the research going, technical research going, this AI safety topic is growing quite fastly with by means of millions of dollars invested. And also strategically, like government level or regulations, also there are research on that. And I can say about two main concerns, immediate concerns and distant concerns. The first one is safety, of course. How do we know how the models behave? What are the errors? What are the downsides? And this, I think, the method is validation, testing, more testing. And for the second one, is more like ethical, fairness, and biases issues. And for that, research now is proposing interpretable AI. I will discuss more about this. And distance concern, of course, popularized by movies, science fiction, artificial general intelligence. Will the machines take over or not? This is the question for distant concern, which I will discuss also briefly. So for the biases and fairness, issues with these uninterpretable models, basically they are black box. We train them over data. They generalize certain information, some statistics about the data, but most of the time we don't know what they are doing. So this is one of the experiments that was done, training a model deliberately on ill-formed data. And what they found was that, for example, they introduced the model only wolves with snowy background, but huskies without any snowy background. And when they asked the model husky image with snowy background, then the model said this is a wolf, but actually it is not. And when they probed the model to see why this decision was made, they found out that the mostly contributing areas of the picture, meaning that the model is giving the decision based on these areas, are basically the background. So it wasn't really paying attention to the object itself, but it is only paying attention whether the background was snow or not. So this is just an example, but we can immediately see what implications might be. Because we are also people in banks, they are using models for credit approval or mortgage approval, and this model might be trained on some data set that might be not very good to represent certain minorities or different people. So in this case, it might make decisions based on not what really need to make decisions, but mostly maybe other properties that we may not know. So in these terms, interpretable AI actually also suggests that we need to find these models that also can be interpretable. Even though if we use black box models, we need to include our cost function perhaps while training or while finding these models. Another objective, which is to find also interpretable model. So we look for the most accurate model with the most interpretability as possible. Yes.
The interpretability in this context.
Yes. So according to different models or approaches, they have different meanings. For example, as I mentioned, the rule-based system is the most interpretable one because the model itself is interpretable. Basically, it consists of rules that can be understood by people. So expert can see, oh, okay, this is why the model is doing this prediction or classification. But if we have black box models, for example, artificial neural network, then there are now new methods coming up how to interpret the model. So instead of only making prediction, we also ask the model to explain why do you make this prediction. So there are certain methods with that. You can even train, perhaps there are research. I'm not really involved in that, but you can also train a network, not only give the prediction, but also explain it with natural language, for example. Oh, this is why I did this prediction. Of course, this is a difficult task, but there is research on that. But for the other part, also if this is one of my colleagues' work, for example, this is a method that can really provide you, like in the image example. Image example was one of the way of looking how the model was making this decision based on which areas that was important. And here is more like what kind of features that played part for classifying this instance in certain label, in certain class. So in this case, you can see, oh, okay, this is classified because of the marital status. So this would help the analyst in the bank or anywhere that that to understand why this decision is made. So this is also another human intervention right now that might be needed, apart from if the result is correct, but also why is this decision is made. And now this is the final part about a bit science fiction becoming real part. Artificial general intelligence. This is also I got from Future of Life organization. So just to clarify some concepts, there are two things like mythical worries that in the movies or some books. and also actual worries that really researchers right now looking into these problems and what it means. So basically only Luddites worry about this, which means that only the people right now oppose this because they are opposing only new technologies. But actual worry is that many also top researchers are concerned with this topic. And also there are some myths about it's going to happen by this date or it's not going to happen by this date. Actual thing is that this artificial general intelligence can happen anytime in decades, centuries, or may never happen, basically. And mythical worry that AI turn into evil or conscious and decide doing something that conflicts with human beings. Actual worry is that AI can turn competent, like it can really have general intelligence like human level, but their goals might not be aligned with ours. So this can also happen in human level, or there are many people that objectives do not align. So people do different things that might conflict with each other. So this can happen on the AI level as well. And another thing is AI cannot control humans, but we know that intelligence can control anything. That we also know from our species that we control, although I think not a very good thing to do, but we control all animals or all other plants, etc. And another another idea is that machines do not have goals, but actual thing is that anything artificial can have also goal. For example, in this case, a heat-seeking missile has a goal. And the most important outcome of this or concern is actually value alignment problem, meaning that the machine, if it has intelligence, it has certain goals that are not well aligned with humans. And here there's a depiction of this goal of AGI and goal of humans. They are not aligned. But I can go back to this example of HAL 9000. I don't want to spoil the movie for you, but in the movie, HAL basically becomes aware of that the other astronauts are going to shut him off, and he wanted to prevent that, not because he wanted to prevent his existence, but he thinks that he is crucial for the mission, and if they turn him off, then the mission will be jeopardized, and he doesn't want to do that. Actually, he has some error, and he's not making a good decision. And he needs to be turned off, but he doesn't understand that, and he needs to exist and keep the mission. In this case, one of the astronauts was lucky to turn him off, but so basically he basically, the way that he tried to avoid that was that he sent the astronaut outside of the ship, but then the astronaut wanted to come back and asked him to open the door, and he said, I'm sorry, I cannot do that. So because you will turn me off and jeopardize the mission. So here we see the example of goal alignment, and there is also many different examples proposed or suggested by other people. For example, we can, curing cancer, we can have a general intelligence and order it to cure the cancer, but it might recognize that maybe if I destroy all humans, then there will be no cancer. Or I can use all humans to experiment on and find the cure, which we don't want. So it should be really clearly specified. But how many of these rules we can classify there is unlimited rules. So this is a difficult problem. There has been some suggestion. One of the most famous one was Isaac Asimov's 3 laws of robotics. And nowadays also there is lots of research, but one of the idea was, or is human compatible AI. The idea is cooperative inverse reinforcement learning, where the agent is not maximizing its goals, but it's maximizing the human goals. And the human goals or objectives of the humans are not known. They are uncertain. And the way that it does is observe the humans and try to understand what their goals might be, and then try to maximize those goals. But this is also a bit tricky, because which goal? I mean, we have goals as the number of people in the planet right now. And if you generalize that, how well you can, and maybe it shouldn't be maybe only human goals. Maybe it should be animals goals and also plants goals, basically planets goals or universe goals. I don't know. Anyway, this is one of the suggestions that is in progress right now. And now I would conclude with this. Basically, 2 observations for interpretable AI. The research right now is encouraging multi-objectivity in the search of models. We need to find models that are also interpretable. And for the second part, science fiction part, is planning ahead. Also, most of the researchers are suggesting to plan ahead. Although it might take centuries, maybe never happen, but we should be aware of this and take safe precautions to make AI beneficial and safe in the future. So with that, I think that's all I can say for now. Thanks. Yes, please.
I have questions. You mentioned that artificial intelligence, in one way or other, will take the role of designers.
Yeah.
Will it be possible in the future that we have completely new kind of mobility, new houses, and all kind of completely different design than with humans?
Yeah. You mean like the designs that human make? Maybe.
How was the car connected to the horse?
Yeah.
Because it was the same kind of thing.
Yeah.
So it's not efficient.
Yeah. Also, yeah, that's true. So basically, the things that we come up with, or we are coming up with right now, is also kind of evolution, where we invent new ideas by modifying the already existing ones, or testing, changing some parts, and see what works. Basically, we are also doing that by ourselves. Like, this is also artificial evolution for us, but it is showing up that we might not be the best designers. So maybe the algorithm we are searching the search space as well as we can, but there might be different designs that we can miss or we cannot come up to yet. So basically, the probabilities are infinite. There is lots of possibilities that in the design space can happen, but we are only maybe discovering very small area that, and also we are maybe optimizing with certain objective, but we are not maybe taking into account other objectives. But with the machine, for example, we can program to take into account different objectives, like maximize, like the example that I give, search the model space, but maximize accuracy at the same time, maximize interpretability, maximize or minimize implementation cost, for example. So a human being to take into account all this, I don't know, 10, maybe 20 objective functions is difficult to come up with. So that's why we use maybe automatized models to automatically discover these kind of design spaces.
Would it be possible in the future that the machines, artificial intelligence, learns directly from nature, how nature functions, and processes, ecosystems, all this kind of?
Yeah. I'm not sure. Probably it should, but if we already come to the point where we have enough intelligence, then we may not need to maybe research more, because we already there. We don't need more inspiration. Maybe it's already done. But if we need more inspiration, we don't know how to do it without getting inspiration from biological neural network, for example, then we should definitely look at it. But if there was a movie again about this, I'm not going to tell more. I said already too much about the other work, the movie. But basically, the idea was that the artificial general intelligence comes to a point where it can discover new theories. Now it produces different theories and proves it, etc., and finds out really new scientific. It really finds new scientific discoveries by either looking at nature or not. But once you get there, then basically you can find everything. like new innovations, new developments possible.
Have you any experience with AI on the financial market?
I did work, I mean, not professionally, but I did do some research on that, where I was, again, doing this swarm intelligence behavior on stock market prediction, where instead of, although I'm not huge fan of it, it was just for scientific curiosity. I wasn't trying to be rich or anything, but the idea was that I was training, for example, with evolution algorithm, different strategies at the same time, not one strategy, but invest many different diversified strategies to come up with some portfolio that can be successful as possible. So I was doing that, but I know that there are many people doing that, this high frequency trading. This is a bit different approach, but I was doing more like learning certain strategy that can be successful. But usually what they do is, actually they don't do that. They do high frequency training, as far as I know, where they really, very like fraction of a second, they make decisions, but not necessarily intelligent decisions. They just want to be the first in this buying or selling option. So for that, they optimize for the speed, not really intelligence per se. But also there are models, mathematical, statistical, that find out what kind of patterns lead profit or something, but usually they don't work, as far as I know.
Still doing that.
Yeah. Although there are, this is maybe pure chance. I don't know, some people are very successful at that. I don't know, it's possible. There's too many people that are losing, so someone should win. Any other question?
Yes. So you didn't talk about it, but I think maybe it's another way to look at how to deal with the value alignment problem. You talk about merging natural intelligence and artificial intelligence. So if we think about AI as extension of human intelligence in some way, would you say that that will deal with the problem of alignment of values, interpretation?
But I think if you consider artificial intelligence as extension of human intelligence, then it would probably cause more harm than good things, because probably people try to benefit from the way that they can by extending their intelligence in wherever stock market or other, in war or resources, basically. It might be that case, but of course we are also progressing in that direction as well. We are aware of many things. Maybe people will try not to do that.
Beyond, qualifying it as good or bad for human evolution, just thinking about the fact that, let's say, we assume that it's inevitable that AI will come, and we have this big problem with AI now, which is that AI doesn't share our values. Maybe one way to deal with that is just merging with it.
Merging with it how? Like cyborg?
Sure. That's one, whatever.
Some people suggest that first this happen, so basically we will modify ourselves. Yes, I don't know if this is a good thing or bad thing. Yes. Thank you.
We already kind of doing this in the sense of hybrid intelligence of AI working together with human beings in organizations, because since we're talking about like different definitions of intelligence, that an organization, a company or whatever is also an intelligence on its own. So in that sense it's already merged with our intelligence, I think. And as long as there's a human check, right, the thing that you post after the misalignment.
Yeah, that's true.
Exactly.
Happening. And I mean, the argument is that it's existential threat to our society or to our civilization, right?
Yeah, well, we're an existential threat.
Okay, there was one more question. question maybe, or should we?
Yeah, I had a question that was a little bit in line with the previous one. What's your opinion about how to harmonize the different approaches we have worldwide? China has different approaches, in the US and Europe. Yeah. At the end, you might have different systems which are not compatible. If I have let's say, a organized system here, and I want to deploy that or interconnect that with a US-based one, you might have a big problem. Yeah. How can you harmonize it?
Well, I think, scientific method can also help here, because we can have simulations of what would happen. For example, we can build a models of whatever social situation is, whatever regulations that we should take. We can build a model. Social scientists also work a lot on these kind of things. So we can build the models of simulating what could happen when this kind of decision is made. When we have simulations of that, then maybe, of course, it's not real world, but we can understand at least what could happen. Then we can take precautions or take a different action rather than doing that one. Perhaps this might be one way.
Really, thank you very much for being here. Innovation Café, we're here every week, and as every week we have the Innovation Café special that you can do for dinner. If you want to, so it's a meat, fish, and vegetarian dish, meat and fish for 70.50 and vegetarian dish for €50. And you can join for dinner if you want. I'll go around like when we're having drinks and I'll ask you if you want to join. I need to double check with the kitchen what the exact anyways. So I'll get back to you. But please join us at the bar for a snack.